So I'm going to be talking about an example again, as I did last time. This time a division algebra case. So remember, there are 9 division algebra cases to worry about. This is one of the prettiest ones, and it's also one which gives quite a lot of fake projective planes. So remember from a couple of lectures ago, we have this general method of making division algebra, or first of all, algebras, central algebras of dimension 9 over a field L by using a sort of artificial field M, which is an extension of degree 3, a Galois cyclic extension of degree 3. And so M isn't unique. You can choose it other ways, but this is a pretty way of doing it. And we define the multiplication so that sigma has this effect on the elements of M, and sigma cubed is an element D, which has to be an element of the field L, and it's particular in this case. It's good to choose a D who's with this property here, because then we get an involution of the second kind on our division algebra. Okay, so this is a division algebra. To see it's not, it's either, you see it's a 3-dimensional, it's a 9-dimensional simple it's either a matrix algebra or it's a division algebra. To see it's not a matrix algebra, you see that it's not, this D is not a norm of any element. You can't write it like this. And to see it's not an element, I gave an argument, maybe in a different example, but it uses a 2-adic valuation. So in this particular case, 2 splits, the prime 2 splits in L because of this, and D is actually a little calculation. It's just row over row bar. So D has the property that if you take a valuation on L of D, you get 0 unless the valuation is one of the two adic valuations. So it's at the valuation corresponding to this ideal, you get valuation 1, and at the valuation corresponding to this ideal, you get -1. Okay. So that's one way of seeing that 2 splits. Another way is to observe that the 2 adics contain a square root of -7. So there are various ways of doing these things. In any case, D is a division algebra. Okay, so remember in an earlier lecture I talked about this homomorphism psi that takes D to the matrix algebra, M, 3 by 3 matrix algebra with entries in M. So apart from this sort of theoretical thing, this is how we realize the elements of our division algebra as matrices. So in the end, our groups are generated by elements of a division algebra, and we can realize them concretely as matrices with elements in just a tiny, not in L, but in a slightly bigger field, M. And because D bar D is 1, there's an involution of the second kind on D, which maps sigma to sigma inverse and takes a complex conjugate of any element of M. And as I did in an earlier example, you conjugate this by, in this case, the element W, which is this. You see, this is, you can think of this as twice the cosine of 2 pi over 7, if zeta is e to the 2 pi I over 7. And the reason you do that is is that these numbers here, when you think of them as complex numbers, are actually real numbers, and they don't all have the same sign. So that this matrix F is, has got signature 2, 1. Okay. So we form, with that iota, we form this algebraic group. Remember, this reduced norm is just the determinant of psi of psi. Okay, and I'm saying here again why we choose to conjugate iota 0 by w. It's because these, when you map zeta to this complex number, these three numbers have different signs, and it would have been neater if they were positive, positive, negative, but in fact they're positive, negative, negative, and so I have to use this. Before I had a delta which was diagonal. Now it's there's a name for that too, skew diagonal or something? Anti-diagonal. Okay, and that has so with that, because of that, it's got this property where, remember, F0 is what I call this matrix. And so a matrix G is unitary with respect to F if and only if its conjugate by delta is unitary with respect to F0. And so you have this, this little diagram here that makes you realize that G of the completion of K with K is Q, the completion with respect to the one Archimedean place you do have on Q is SU21. So if you unravel all the definitions, that's what this gives you. And that's one of the key properties you need of your division algebra. It's got to be here we've got K, the field K is Q, and there's only one Archimedean valuation. And when there is only one like this, you require that the GV is congruent to SU2, is isomorphic to SU21. When there are two, you want the other one to you want this to be isomorphic to SU3 for the other Archimedean place. All right. So we're looking for fundamental domains. We're looking for fundamental groups of fake projective planes. And so we're going to take a principal arithmetic subgroup. So it looks like this. And in the one of the lectures, I showed how this is an important equation that comes out of, which is effectively in Prasad and Jung. And in this particular case, the alpha is 2 because we're in a division algebra case. And for this particular pair of fields, K and L, we know that DKL is 21. The set of places is corresponds to prime numbers, okay? And so this formula becomes this, where T is a finite set of primes. And so because the because the division algebra, where's that eraser gone? Ah, over there. So the fact that this division algebra behaves in this way tells you that 2 is in 2, 0, and D0 is, the division algebra is chosen so that this set is precisely 2. Anyway, so you get a one of these factors here comes from Q equals 2. that factor is this, which works out as 3, and so you cancel one of the 3's and you're left with this equation. Okay. So we have a diagram. Oh, okay, no, I've got to wait a moment. Oh yeah, so I want to look at the possibilities for these factors here. Okay, so I've gone through some of this already. If Q happens to split and it's in T, that forces Q squared plus Q plus 1 to divide this, and so it has to divide 21, but that never happens. If Q is 2, that's not allowed because that's in T0. Q equals 3, you get the answer 13, and so on. So very quickly you see that this can't happen. If Q, different from 7, now I have to talk about 7 separately. If Q doesn't split in L, then this factor has to divide E prime of PQ, and so it has to divide 21, but there are a couple of possibilities here. Q equals 3 and Q equals 5, when you get 7 and 21 respectively for this expression here. And so 3 and 5 can be in T. They can't both be there because that would mean both 7 times 21 divides 21. It's no good. So the possibilities for T are that, well, it could be just T0, could be just 2, or you could add 3 or you could add 5. So these are the 3 possibilities for T. And when for example, 3 is in T, that means that the parahoric subgroup has to be a maximal, it has to be a stabilizer of a type 2 vertex of the building associated with okay, so this group has a building associated with it. It's because those primes are primes which don't split in L. The building is a tree. The tree has vertices of 2 types, and in order to get a factor, you get a factor like this when it's PQ is a stabilizer of a type 2 vertex. Okay. So this prime 7 has to be treated a bit separately because you see it ramifies in L. It's I won't attempt to give you a. It's simple to see that it ramifies in this particular cyclotomic field. 7 ramifies there, and so so the building you get associated with this thing in the case Q equals 7 is not just any old tree, but it's a homogeneous tree in which.
Actually, you're looking at L, which is Q of root minus 7.
Oh yes, of course. Yes, so L. Yes, of course. It's really obvious that it ramifies. Yeah, sorry, I was of course thinking about which will come up in the next slide or something. Yeah. Yes. So, so 7 is minus s squared. You see, so that exhibits the ramification of 7. Okay. Anyway, because 7 ramifies this building that we're being vague about, but there's a building, and it's just, in this case, it's a homogeneous tree, and in which every vertex has 8 neighbors, and 7 doesn't make a contribution to Prasad's volume formula, co-volume formula, but P7 can be the stabilizer of a type 1 vertex of this building, and it can be the stabilizer of a type 2 vertex, and neither makes a contribution to the co-volume formula, but you get 2 non-conjugate groups. Okay, so that's important because, well, these are classes are up to conjugacy, you see. So what's really important for us is not the set T, but the set T1. It's the set of primes which don't split in L, and for which P sub Q is a stabilizer of a type 2 vertex. Okay, so in a previous slide, we had 2, which is in T, but 2 doesn't appear here. It's not relevant to this discussion. Okay, it's the ones that for which PQ is a stabilizer of type 2 vertex. So the possibilities. So you can have nothing. You can have 3. You can have 5, and then you can switch from P7 to P7 prime, and then you get it. So P7 prime is a stabilizer of a type 2 neighbor, type 2 vertex of that tree. And then when you choose P7 prime, did I call it a name? I didn't give it a name. When it's a stabilizer of a type 2 vertex, then it falls in T1, and so you get these possibilities as well. So that's why there are 6 things to worry about. So I'm going to concentrate on the first 2 cases, in fact, mostly on the first case. All right, so I didn't quite get through finishing explaining this in lecture 2, but I'm not going to go into. It's on the web, I guess, that talk. So if Q is a prime which splits and is not 2, then the algebraic group G, its QQ values, QQ points are isomorphic to SL3QQ. And we can choose our maximal parahoric to be SL3 of ZQ. So this is a nice compact, maximal compact subgroup inside SL3QQ. Okay. So that's we just make that choice of our parahoric for each of the Q's which split, except for 2. Remember, the way it's set up, because this is a division algebra still, GQ2 is compact, and we're going to choose P sub 2 to be, we want it to be a maximal compact subgroup. So we choose it to be the whole thing, you see? So that's what happens with 2. Now, when Q doesn't split, you get different behavior. The algebraic group at these points is now actually a unitary group still. Okay, so you get a form which depends on Q. I've called it FQ dash. And so that's at the end of my second talk, which I didn't get up to, sorry. But anyway, you can arrange it so that this FQ prime has entries, and an inverse has entries in the valuation ring of the, you see, so Q corresponds to a valuation on the rationals. Q is not splitting, so there's a unique extension, which I pedantically call Q tilde, to this field. So the completion of L with respect to that valuation is none other than QQ with S adjoined, this square root of -7. And so this is the ring of elements whose valuation is at least 0. And you can arrange that this matrix here is in here. So I'll actually exhibit for Q equals 7 that matrix in a moment. So you'll see how this works. And alternatively, you can look at the back end of my second talk.
This implies that the OQ lattice L equals BQQ?
That's the mouse. Yeah. I had that problem the other day. Okay. Okay, so the point of this here is that, so Tim talked about how you take duals of lattices. So we're playing with, we've got this field, which is the cube power of this, and we're looking at lattices with respect to this subring, this compact subring, and here's the most natural choice of lattice there. And by getting fq prime in here, that makes this lattice self-dual, where the dual of a lattice is defined in this way. Yeah. Okay, so there's a form. Anyway, it's a fairly standard sort of dual thing. Okay. So what we're going to do is we're going to choose this lattice is our vertex in the building, which is stabilized. We're going to choose our maximal parahoric to be the stabilizer of that vertex. Okay, so remember, the vertices are lattices. They're lattices, which are either self-dual or something more complicated. And this is a type 1 vertex, and we're going to choose Q sub Q to be P sub Q to be the matrices which have entries in the valuation ring and which are unitary. Okay, so this is the group. This is a group of elements of which stabilize the particular lattice, the most natural lattice there is. Okay. Okay. So then we form this principal arithmetic subgroup. Okay. So on each occasion we have chosen a type 1 vertex of our building. So we never choose a type 2 vertex, so the T sub 1 is empty. We have 6 possibilities for T1. This is the case when it's empty. Okay, so we had a diagram. I like this diagram. We have, this is the DKL. This is this is of index 3 to the alpha in the normalizer. So alpha is 2 whenever you've got a division algebra. And so pi is a hypothetical fundamental group of a fake projective plane, or a fundamental group of a hypothetical fake projective plane. And so basically you want to get a strong grip on this group gamma bar, the image of gamma under the natural map. So we want to get a presentation of that group, understand it well enough so that we can work out what subgroups of index 21 we have. Okay, so that's the goal. So let's look at an element of our division algebra. I've written it in a slightly screwy way, so my j goes from 1 to 6 instead of the more normal 0 to 5. But anyway, I've done it like that. So we want conditions on the coefficients in order that psi belongs to this particular principal arithmetic subgroup. Okay, so it means you've got a condition at every q. You want that, it maps across to an element here. This is in D. And, well, here I'm sort of skating over I'm trying to avoid this business about the adjoint group. And I want to sort of minimize the algebraic group stuff. So I'm just going to work with G, and then I have to sort of fudge a little bit. But anyway, we need the normalizer of gamma as well as just lambda. And so we need, what that means is we need to find, we need to look at the psi as satisfying this, which don't necessarily have reduced norm 1. Because, basically because they will normalize the lambda. And one can see that that's all there, that gives you the full normalizer.
Oh,
I'm getting slightly lost.
Yeah.
Isn't zeta a seventh root of unity, or is zeta a different?
Oh, this is C.
This is C. This is a seventh root of unity. Yeah.
So why are we only going from 0 up to 6? From 1 to 6?
Satisfies the 730 equation.
Yeah, because it satisfies 1 plus zeta to the 6 is 0. You see, so you can eliminate.
So we seem to have only got to the power 5.
Yeah, that's right. Yeah, because of this, you see, you just don't need it.
Using that equation. Okay,
Yeah,
good.
yeah,
I'm sorry.
yeah.
I'm sorry,
I'm pleased that you asked the question, though. So anyway, it's a cute fact out of cyclotomic fields that if M is a cyclotomic field, then its ring of integers, the ring of algebraic integers, is none other than this. You see, you just need integer combinations of the zeta powers of zeta, and you don't need any because of this. In this case, you only need to go up to 5. Okay. All right. So basically, we want to understand when an element is in lambda. In terms of, we want to understand what that means in terms of these coefficients here. Okay. So because I'm allowing things which aren't necessarily of reduced norm 1, I'm fudging here a little bit. So anyway, we have a zeta, we take its image, which will be in here when Q splits, and we want to know when we're actually in here. Similarly, when Q doesn't split, we get a thing which has entries in QQS and is unitary with respect to this form, and we want to know when it's actually got entries here. Okay. So if I were being more precise, I'd be working with lambda, and then we've got an SL there, an SL there, and SL and SL. But I'm skating over that. So the condition for being in PQ is mostly the simplest one you could imagine, that the coefficients aij have no q's in their denominator. Okay, this is something to, it's just a little, it's not a completely obvious fact, but it's true, that if q is different from 2 and 7, in order for the image of psi to be in here, you just need that there are no q's in the denominator of the ajk. One has to do a little bit of work to see that. It's not hard, but it's not completely obvious. And indeed, when q is 7, it's not true. So when q is 2, this is compact, and so there's no condition in the two-adic place, and 2's are allowed in the denominator of the ajk's. So now I want to stare at the case q equals 7. Okay, so this is the slightly more complicated situation where our field, so auxiliary field M, doesn't embed in Q7 of S. Life is a little bit easier when it embeds. And we want to be sure that there's an element eta whose norm is D. This is part of the proof that so let me get this right. So we're dealing with a Q that doesn't split, and this is isomorphic to the 3x3 matrices over. And to see that, I explained in one of the earlier talks that you need to get a norm. You need to realize that D is a norm. Okay, and it's good to have this too for reasons I'll explain in a moment. Now we've got this big theorem from class field theory, which tells you that very often you know an element D is a norm just by checking its valuation. Unfortunately, so here's a case where I do have a little complication of ML. This extension here ramifies, and so you can't immediately use that norm theorem. But what we do is just grubby calculations and work out an element whose norm is D. And if you can actually choose an element, not of the bigger field, but of just this, whose cube is D. So you realize D is a cube. So if you go looking for a cube, you just write, you might write it down as C plus ds and set its cube equal to D, capital D, and solve some equations. And you can eliminate D, plus put in this condition. You can eliminate D and you find it's 8c cubed minus 3c minus 4 all over 7. It's just an elementary thing. So you can find a solution eta. And of course you need to know, the C has to also satisfy this. And then these two things hold. And then you need to know there is a C that does that, and there you use Hensel's lemma to check that cubic polynomial has a root. Okay. So this is an ingredient of the proof that the fact that D is the norm of something in this bigger field tells you get that. You get the division algebra splits. And then the isomorphism you get is seen using this isomorphism which I mentioned. And this isomorphism is obtained by taking your D, embedding it in the 3 by 3 matrices over M. M is Q with zeta adjoined. So it sits inside Q7 with zeta adjoined. You see, so you get an embedding there. And then by conjugating by this J, which is something I used the other day, where this is the eta whose norm is D, and this is comes from a basis of M, you find that this maps D not into elements with entries here, but into matrices with elements in the smaller field, Q sub 7 of S. Okay. Okay, so anyway, you have to do this. This is sort of what you have to do with half the time when Q doesn't split. When it depends on whether M embeds in So this is a situation where M does not embed in here, then you have to go through this conjugation by J business. If it does embed, if this does embed in Q sub Q of S, then you don't need to worry about that conjugation by J. It's easy. Life is simpler. All right, so when you unravel everything, you find that an element which is unitary with respect to iota goes across to a matrix which is unitary with respect to this thing. So it's a tedious a simple calculation. You follow your nose. Okay, so however, in this particular case, something quite cute happens. Because because eta is 1, that C of the previous slide, its adjoint is equal to its inverse. And so C is a diagonal matrix, F is a diagonal matrix, everything commutes. And so this part goes away. And so I chose this word here rather than cunningly because adroit is such a lovely French word, and here we are in France. So by cunningly choosing this particular basis of M over L, you find that so you've got this J star inverse F J inverse, and this is theta star inverse C star F C inverse this, and then these go away because as I mentioned up the top, and so you get something actually which doesn't have any, doesn't depend on the valuation, and by choosing this particular basis, at least after multiplying by 7, you get something which is has entries in the number ring, OL, and determinant 1. So remember, what I needed was that the image, which the thing I called this, I need this to be in GL3 with entries in the, I need it to be entries in there, you see, and I've done that in spades. I've got, not only is it got entries here, it's got entries in O sub L, in the number field, and determinant 1. So it's not only in GL, but it's in SL. Okay, anyway, all I really need is that it's in here, and that makes this lattice self-dual. So, how are we going for time? So back up here, we have elements of D and they're mapped across to matrices. And so I want to do that in the case, oops. I want to do that in the case of Q equals 7. So I want to take an element of D, which is unitary with respect to iota, look at its image and ask, so I get something which is unitary with respect to F prime. I want to know when it's in, when it fixes this standard lattice. I want to know when it fixes this. So that's what zeta 7 looks like, psi 7 looks like. And you see it's got entries in this matrix, in this field. So that means its entries look like this, where the xij and yij are numbers in Q7. And you can do a little bit of computer algebra, or probably by hand, and you can work out that these xijs and yijs are all linear combinations of the coefficients that came from psi, the 18 coefficients that you have with psi. So you get x is ma, where a and x are column vectors of length 18. The a is the vector of a's, and the x is the vector of x's and y's. And you can actually write down m explicitly in terms of there's a element c of the 7 at x which is lurking around because it comes from c. Okay. Anyway, you can work out m completely explicitly, and we're interested in when this zeta sub 7, psi sub 7 fixes this lattice, and that's well, it's not obvious, but it's because it's if and only if psi sub 7 has entries in that valuation ring. The valuation ring consists of the obvious thing, the sort of x plus ys, where x and y are as in Z7. And so what it means that this xi sub 7 fixes this lattice is that the xij's in the previous matrix and the previous slide are all in Z7. And that means that this vector has entries in zeta sub 7, in z sub 7. Okay, so I should be cunning and have one of those things which reveals the bottom half only later. But so the bottom part is another thought. Okay, so this is a crucial thing. So in our web pages, we have these matrices M, or rather, in this case, 7-adic approximations to mod 49 or something. They will appear in, they'll be available in that web page somewhere, so you see that. But since I put those things up on the web page, I had the following little thought, that we can simplify this matrix M by bringing it into reduced row echelon form with respect to, so if you have a matrix, an 18 by 18 matrix with elements in Z sub 7, this has entries in Z sub 7, obviously if and only if LM has entries in Z sub 7, and you can choose L so that LM is in reduced row echelon form. And so after all that, you find that the condition for xi sub 7 to fix this lattice is that a certain very simple matrix E, 18 by 18, I mean, but nevertheless simple, matrix has entries in Z sub 7. So it's a little bit more complicated. If there weren't a capital E, if there weren't an E, then we'd just be asking that there are no 7s in the denominator. Okay, but we have this little wrinkle. We have to multiply by a matrix and then ask that there are no 7s in the denominator. Okay. All right. So you take M and you take an approximation, mod 49 is enough, and the following Magma command is, you take those approximations and that ... is a string of 18 by 18, is that 300 and something numbers, and you let M7 be the matrix of approximations, and you issue the command echelon form, and out pops the answer, which is this. So it's a very simple matrix, and I've used a certain order I've used this order on the A's, and you can see that if I just fiddle that order ever so slightly, I could move that 7 down to there, and then the matrix would even be simpler. And indeed, I don't understand why this, but I could do a right multiply by an integer matrix and make this, in fact, just diagonal 1, 1, 1, 1, 1, and then 7, 7, 7. But I don't see a whole lot of point in doing that, so I didn't. Okay, so to summarize, for each prime q other than 2, this is our maximal parahoric, and for each q which doesn't split, this is our maximal parahoric. We've formed this lambda, and we're looking at the elements xi of this form, which are unitary with respect to iota. Then in order to be in lambda, so in order that this happens for every q different from 2, you need that the aij's have no q's in the denominator for any q other than 2 and 7. So fancy way of saying that is this: you're allowed 2's, you're allowed 7's in the denominator, but there is a strong condition on the 7's in the denominator. Okay, so after multiplying by e, there are no 7's in the denominator. So this is sort of preliminary work in order to...
Now we can get started.
Now we can get started, yeah, exactly. So we're trying to find elements of lambda, right? And they look like this, with some arithmetic conditions. So these are the arithmetic conditions. There are no primes in the denominators except 2 or 7, and that after multiplying by e, you have no 7's either. in the denominator. So here I'm going through this fudge business about when we want the normalizer, we want the image of the normalizer, and so we're looking at xi's which satisfy this, but no longer the norm condition, and the conditions are the same, except you work modulo the scalars of the right sort. So this is actually the setting we work in. We look for xi's of this xi is satisfying this with these arithmetic conditions. Okay. So how do we find these elements? So in the case of the matrix algebra, there's a nifty method that I explained the day before yesterday, which involves the right column in the first row and filling in a matrix and stuff. And it goes lickety-split. Once you write down the program, it runs in a microsecond or two, and you get a whole bunch of matrices very quickly. In this case of the division algebra, I don't know how to make anything like that work. So we use something called a Cayley transform, which you're familiar with from complex analysis. So if you have an element of the division algebra which is skew Hermitian in this sense, it can't be 1 because 1 isn't skew Hermitian. So that means 1 minus eta is invertible because we're in a division algebra. And so we can form this element. And when you apply you apply iota to this and multiply it by itself, you see eta is mapped to minus eta, and everything cancels and you get 1. So this is a way of cooking up elements which are unitary with respect to iota via the skew Hermitian idea. Okay. Now the good thing about that is that this is a linear condition, whereas this condition here is a nonlinear condition. So let's write down an eta with coefficients s for skew, s sub jk. So this condition allows you to impose 9 linear conditions on the 18 variables and bring it down from 18 to 9 variables. Okay. Now, they're rational in theory, so to avoid rational numbers, want to work only with integers, we just introduce a d here. Okay, so when we are looking for elements psi of lambda, so they're the ones with reduced norm 1, that means that the reduced norm of the numerator has to be the same as the reduced norm of the denominator. Okay, so when you write that condition down, you find that there's a cubic condition in the Sij's or Sjk's. It's a cubic condition, which I call, so you've got 9 variables Sjk left, and when you write down the difference between this reduced norm and this reduced norm calculated, you find you get a cubic, multiplied by s, as it turns out, but anyway, a cubic. Now we're also interested in elements of the normalizer, and these will have reduced norm which are plus or minus powers of d, where d is 3 plus s over 4 that we work with. And so then we're looking for elements eta which are skew Hermitian and satisfy this. So that gives you another condition, which I call con B. So we then set a computer running through 9 variables Sjk and the variable d, and ask it to satisfy the cubic equation. So there are 2 programs to run, one with setting condition A to be 0 and the other setting condition B to be 0. And every time you get a solution, you plug the Sjk's into into this and work out the AJKs and ask that they satisfy the arithmetic conditions. So, that there are no primes in the denominators other than 2 and 7, and that E times the thing has also got no 7s. Okay. So, these conditions are time-consuming. Even with only 9 variables, when you write down this cubic, it goes for several lines, and so it's so deep inside the computer, inside the loop, and you don't want to calculate this any more often than you have to, okay? Because it's a biggish thing. Fortunately, and I'm going to be vague here, there are strong necessary conditions on the SJKs, so that you actually only need to calculate a quadratic polynomial, the bitrace of, as it's called, that means the trace of the adjoint of the matrix on the SIJs. So in the program well, there are first of all some elementary congruence properties on the SJKs, which allows you to maybe only look at 1/8 of the possibilities. Then you calculate this bitrace, and then you apply these necessary conditions, which are, again, linear conditions. And so the upshot of that is you only calculate these cubics in a tiny proportion of the cases. So it actually goes okay. And this is particularly important because when you're dealing with K different from Q, you start with 36 rational variables. After this Q trick, you're down to 18 variables and plus D, so you're at 19 variables. And so you've got to have everything pretty efficient for this to work. So in this particular case, when T sub 1 is empty, by running a program, it's hard for me to say how long it took, but I ran it again, but I knew the answer, you see. So I knew I'd set my variables going from -10 to +10 or something like that. But before that, I might have had to set it running over larger ranges. And so I had my computer cranking away for a long time. But in this case, you only need to, you get pay dirt by going up to 12 and by choosing D to be 7. And if I put in that, I can actually make the thing run in an hour or so. It comes out quickly. So you run this program, run these 2 programs, you get a few hundred elements, and you can just see that your output is, every element is a word in these 2 elements, where for this particular B. So it looks like the group is generated by Z and B. Okay, so I mean, obviously, I ran it over more than one night, and I ran it, over weeks perhaps, or no, maybe not weeks, but over several days, let's say, and got more output. And every time you could see that your output was a word in Z and B. And so it seemed awfully likely that Z and B generated the group. So this is now intersecting with what Tim was talking about. You start with the output of your search programs, and you have a set of elements, and you choose some D1, maybe to get to a range that you have no more than 10,000 matrices, something like that. You choose D1, and you thicken up S. You thicken up this output by adjoining any inverse. If you've got a G in the set, you adjoin the inverse. If you find 2 G's in the output and calculate this distance, if it's still underneath D1, you throw GG prime into the list as well. As Tim said, throwing off the last one if you're full. And you form this sort of fundamental domain, and and here's where Tim is hopefully going to talk about this tomorrow. Calculate this number here. Okay, so in fact, Tim can calculate this program And if it turns out, Tim's talk last hour had R1, not D1, but apart from that, that's if you've set D1 big enough, and if you can calculate R sub 0, then you have all elements which move the origin at most D1. That's what Tim talked about last hour. And that has the following consequences, which he talked about. Once the same condition holds, the set you've got generates gamma bar. The fundamental domain F sub S corresponding to S is actually the full fundamental domain of the group gamma bar, and you get a presentation of the group just by looking at the relations of the form G1, G2, G3 equals 1, where the GIs come from S. Okay. So that page overlaps. Okay, I better keep on going. So in this particular case, these elements come in double cosets. There's a subgroup of size 7 generated by this diagonal matrix Z, and so you apply Tim's calculation of the R0 and the theorem about D1 being more than twice R0 to this set S, which has a sort of chunky number of elements, and these are, to be completely specific, these are the double coset representatives. So B, for example, has reduced norm D. So when you multiply by the inverse of D, which is this, you get reduced norm 1. So I've got these factors D kicking around to arrange that the reduced norm of these elements is 1, and the reduced norm of these elements is D. Okay. So this is the set S to which the previous talk applies, and you apply that theorem, and you find that gamma bar is indeed generated by Z and B, and you get this presentation. I expect that some of these relations can be removed. Yes?
So did you get this far just by asking Magma to improve it, or did you apply your own brain?
Yeah, well, there's a Magma routine called simplify, which allows you to simplify the presentation. But I suspect, and then I fiddled around by hand, being cautious because it's a place where you could easily introduce a mistake. However, Carlos told me about one of the Magma programs called Find Isomorphism or something. And so I could say maybe remove that last one and ask whether the two groups are still isomorphic. So I expect I can remove a couple of those relations. Anyway, the fact is it's simple enough. There are just a few, less than about 8 relations there, and so it's something that Magma's set up so that it does a lot of calculations with finitely presented groups. And here we have a finitely presented group whose presentation is not too bad. And then Magma's got a command low index subgroups. This is the syntax of that command. If G is a previous thing, and it tells you, it lists the conjugacy classes of index 21 subgroups. In this case, you get 3. And it's got a routine called abelian quotient invariance, which calculates the abelianization of each of these groups, and you get those finite answers. Okay, so that's one of the properties that the fundamental group of a fake projective plane has to satisfy. It's got to have B1 equal to 0, so that means this has got to be finite.
So I think that first one is the one that Guillaume was talking about yesterday.
Was it? did you have one whose abelianization was order 16?
Yes.
Yeah, okay, well, that was probably it then. But anyway, okay,
This is the one we got.
yeah. So anyway. Then you also have to check that these groups pi are torsion free, and that's easy when you have a set of conjugacy class representatives for the torsion elements, and every element of again, if this happens, then S contains every element of finite order is conjugate to an element in S. And so S is a set of only 987 elements, and so you just run through and work out which ones have got finite order. Okay, so the upshot of that is we get 3 fake projective planes from this particular thing in this way. So I've probably got 0 minutes left. So I wanted to tell you what happens if I replace the P7 by the other P7, the P7, which is the stabilizer of a type 2 vertex. And what you do is you simply choose a simple matrix C for this particular C, and this is again a lattice, and it satisfies a bunch of simple properties, and that means that this lattice satisfies this, which means it's a type 2 vertex, and you leave all the other P sub Q's the same, and you ask what it means. You replace all the QQs by, you don't change any of the other QQs, but you replace P sub 7 by this one, and you look at an element of the division algebra satisfying this, and you ask, when does it fix this lattice? And very similar calculation gives you another 18 by 18 matrix. I think I've even got it here. Look how similar that was. So there's another E. It's actually almost the same, isn't it? It's got its non-zero stuff in just the same spots. And so the same method, you get a presentation, and this time you get 4 index 21 subgroups, and you can check that they're torsion-free and have finite abelianization. And this one is, this last one is particularly interesting because it's is Mumford's original fake projective plane, or the fundamental group thereof. Okay, I'll stop. Sorry, I ran over time a little bit.